All right, now for the joy you all have been waiting for is actually some real world application for quadratic functions. I just want you to think about it. Think about any time you see something that might go in an arch like this. I mean, think about a basketball that's being shot, or a ball that's being tossed, a football that's being passed, or a football that's being kicked. Those types of things. You see that shape modeled in a lot of different situations. A rocket being launched, all kinds of things. So you might notice that this would be a definite more real world application, especially for it to be upside down more than right side up. So suppose you launch a model rocket. Let's kind of go ahead and talk about this. Number one, with an upward starting velocity. So we have to actually know what our starting velocity is. And we can use this equation right here. Okay, right here. And the negative 16 t squared has to do with the pull of gravity. So we can use that equation to find the rocket's altitude, h, which is its height. And the h represents the height in feet, and t represents the seconds after launch. And then that little h sub 0 is called an h naught. Okay, h naught represents the initial height, the starting height from wherever it's launched. If it's launched right on the ground, it'd be a starting height of 0. If it's launched on a little table that's 3 feet above the ground, so that type of thing is your initial height. So suppose the upward starting velocity is 315 feet per second, and the initial height is 3 feet. When will the rocket hit the ground? So the first thing we have to do is substitute in the information that we know. So and write our quadratic model. So the height of our rocket is negative 16 t squared plus, well, that v right here is for our velocity, and our velocity is 315 t. And then our initial height, or the h naught, is 3 feet, because we are starting 3 feet above the ground. So I want you to kind of picture this, and it's wanting to know, when is the rocket going to hit the ground? So I want you to picture the coordinate plane, and picture the parabola that might look something like this. Okay, that's not a great parabola, but we're going to say it like this. So my initial starting height, I'm not right on the thing here. My initial starting height would be right there at 3 feet. Okay, so the rocket goes up and then gradually, because of the velocity, then the gravity eventually pulls it back down to the ground. So right here is where we're looking. We're looking when our height is 0. Think about this. When it hits the ground, the height above the ground is 0. So that's when we would substitute that 0 in, because that's what we're looking for when the height is 0. Now we just have a quadratic equation that we can plug into Desmos graphing. It would be a great strategy to plug in Desmos graphing. I'm actually going to pull Desmos graphing up, and I'm going to show it to you. So here's the Desmos that I've kind of pulled up. Now you can't see the top of this arc because it's just, I mean, I could scroll down. I mean, the top of the arc is way, way, way up here, because it goes way up, kind of curves a little and comes back down. I really want to focus on this point right here. Okay, that point right there. That would show me when that rocket is going to hit the ground, and it's going to be about 19.7 seconds after it launches, it's going to hit the ground. That's the key right there, 19.7 seconds. So graphing it on Desmos is helpful. Notice right here, there's my starting height. When the rocket launches, 0 time has passed, and I'm already 3 feet into the air. And right here, my height is now 0, and this much time has passed. So just keep that in mind as we go through this. So that would be for that problem, that solution. So let's go ahead and look at the next example. And I can go to Desmos and again graph it if we need to. So the height of a projectile can be described by the vertical motion model. We already have that. They did not use the h naught this time. They used s for the starting or initial height, the starting height, initial height. Other than that, it's the same. Just keep that in mind. That spot will always be your initial starting spot. So the height of a projectile is that model. The Everything else is the same. V is the initial vertical velocity. To catch a frisbee, a dog leaps into the air with an initial vertical velocity of 28 feet per second. Okay, so let's think about this. It wants me to write a model, which is basically the algebraic model. So the height of the dog equals negative 16 t squared plus his initial velocity, okay, of 28t. And then what about his starting height? Well, think about a dog. A dog is going to be on the ground when he starts, and he's going to leap, catch the frisbee, and come back down. Or maybe he's going to leap up and catch the frisbee and come back down. Okay, it may not be so arced. I don't know. I just am showing it that way. So his initial starting height would be 0. So we don't really need anything there. We don't have to have anything there. So there's my vertical model to show the height after any amount of time. I can figure out what his height is. After how many seconds does the dog land on the ground? So again, we're back to that. When does he come back down to a 0 height? Well, since we don't have a c, since we don't have a constant or a c, I can just factor this one out. This one's easily factorable. They both have a common factor of negative 4t. So I can take that out. I'm left with 4t minus 7. So I know that I then can say negative 4t equals 0 or 4t minus 7 equals 0. This one's going to give me just t equals 0. Well, we know that when the dog starts out, he is literally, let's think about this. He's literally at 0, 0. 0 time has passed. He's at 0 feet. He leaps and he comes back down, catches the frisbee. Okay, so that one is going to be his starting time. We don't want that. No, obviously some seconds have passed. So this is going to be my actual correct answer. So I'm going to have 4t equals 7. So t equals 7 fourths, or if I want to look at it this way, 1.75 seconds. That's when he's going to hit the ground, because 7 fourths is 1 3/4. So 1.75 seconds later, he's going to catch that frisbee and hit the ground. That's a pretty quick jump. All right, next problem. Henry launched a model rocket with an initial speed of 88 feet per second. So there's our 88 feet per second. There's our velocity. After how many seconds will the rocket be 40 feet high? So that's what we're asking this time. So notice I don't have an initial starting height. So that means that the rocket was on the ground. So the starting height is 0. And then we're going to go up and down. I really need to adjust my I need to calibrate the board. So I know that the height is negative 16 t squared plus 88t. So there's my model, because all I did was put my velocity in right here, my velocity in. That is so off. My calibration is so off. But it's asking me after how long, after how many seconds. So I'm trying to find t when the rocket will be 40 feet high. Well, this is height. I'm looking for height. So they would go in right here. And ironically, this becomes a system of linear equations. I don't really want to explain it, but because we're going to do this on Thursday, or probably Thursday or Friday. So I want to look at it like this. So here is 40, and here is my calibration is so off. Here's my line, y equals 40. Okay, that's my line. I want to know when that rocket is going to be 40 feet high. Okay, and it might be 2 times, might be 1 time, it just depends. But I'm going to be looking for when that parabola intersects that line, y equals 40, when the height is 40. So that's how this becomes a system of a linear equation and a quadratic equation. So the first thing I have to do, I can't solve this until I have this side equal to 0. So I'm going to subtract 40 from both sides. Now, the last thing I want to do is to make this a little bit easier. I noticed that the negative 16, the 88, and the negative 40 all have a common factor of 8. So I'm going to divide everything by 8. And I could divide by -8, but it's not really going to matter. Okay, and what I'm going to do when I go to Desmos though, I just want you to know I'm going to graph this one in Desmos, and then I'll show you how to work when I graph Desmos. So then I end up with 0 equals -2t squared plus 88t minus 40. And we're going to look at graphing this a couple of ways in Desmos. Okay, I pulled up the Desmos graphing calculator and I graphed this, and I just want to, let's go ahead and zoom out a little so you can kind of see the path that I did. First of all, here's what I typed in. I typed in the original equation so that I would make sure I'd get my parabola right here. And then I typed in that horizontal line y equals 40. And I want to see where these two intersect. So that's what I actually looked at. So I'm going to go ahead and take this off. And there's the parabola and the line. So let's go ahead and now zoom in to where the height equals 40. So we can kind of look. Here's one spot, and here's another spot. So half a second into it and 5 seconds into it. So that gives you the answer, showing you where they intersect. That's what we're looking for. After how many seconds will the rocket be 40 feet high? They would have two answers, a 0.5 seconds and a 5 seconds. So that would be my answer, because it's going to be 40 feet high twice. Okay, all right, let's look at, suppose you launch a firecracker with an upward starting velocity of v feet per second. You can use the equation that they've given us, the h naught, to find the firecracker's altitude after launch, t seconds after launch. Suppose the upward starting velocity is 185 feet per second and the initial height is 2 feet. At what time will the firecracker be at its maximum height? What is the maximum height? So what we're looking for here is our maximum height of the firecracker. So we're looking for the vertex. All we're looking for is the vertex. So let's go ahead and make our model. So the height equals -16t squared plus 185t plus 2. And it's wanting to know what the maximum height is. So to find my vertex, let's remember that we do -b over 2a, and that gives me my axis of symmetry and the x value of my vertex. This gives me both. So none of these have any kind of common factor, which it doesn't really matter because we can't really factor out that kind of stuff. So we're going to do -185 all over 2 times -16. All right, so at what time? We're gonna round to the nearest 100th. So I'm going to put this into the calculator, and I'm going to divide -185 divided by 2 times, oh, I'm just going to say -32. Divided by -32. So approximately, I'll round to the nearest hundredth, 5.78. So that will be the time, 5.78 seconds. And then the way I find the height is I just substitute that back in. -16 times 5.78 squared plus 185 times 5.78 plus 2. So we're just going to type that into the calculator as well. -16 times 5.78 squared plus 185 times 5.78 plus 2. And the height is approximately 536.77 feet. So that would be my vertex. And if we graph this, again, you could graph this on Desmos and you would show that. And I'm going to actually pause the video and I'm going to graph this on Desmos and show you, and that'll be the end of the video. All right, here's the parabola. As you can see, I have it scaled way in so you can see the top of it. So I'm going to actually go ahead and zoom in a little bit so we can actually see the vertex a little bit better and get a point. Hopefully it'll be the same answer as we have on our paper. So 5.781 and 536. Let's check out what we did. 5.78, yes, I agree. And 536.77, so let's check that. 536.77 and 5.78. We did awesome. So Desmos is very helpful, but it wasn't too hard to find otherwise.